So welcome everyone back to the second session, second block of talks. We're very excited to have as our first speaker, Dr. Stefanie Jegelka. Did I pronounce right? I hope. And she is a faculty at EECS at MIT in the CSAIL area and has been really pioneering amazing work in the area of graph neural networks. So thank you very much for joining us. We're excited to have you here.
Thanks a lot, Adam, for the introduction, and thanks to all organizers for inviting me here. That's a super interesting workshop. So today I would like to talk about our work on looking a little bit at representational power and learning in graph neural networks. So before we go there, let me just motivate the learning with graphs by showing you a few applications of where graph neural networks and learning with graphs actually comes up. So my first example are cases where the input is a graph and you would like to predict something about that graph. So a currently very popular example is that you have a molecule and you're trying to predict whether this molecule would be effective as a drug for COVID, for example. And so there's lots of small molecules where people are trying to do these predictions to basically improve the screening for new drugs. And this can be equally used in material science and other kinds of computational chemistry for just screening materials, trying to predict whether they would react in certain ways, etc. So here the input is a molecule which could be viewed as a graph with attributes. So I know something about nodes and I know something about the edges in this graph, which are the bonds. As a second example, I may be looking at social network analysis. And instead of trying to predict a label for the entire graph, I'm trying to predict a label for a node. And basically here I'm looking at the node's neighborhood and sort of trying to use information from that neighborhood to predict that node's label. And so in a social network, this could be trying to predict some interests of a person or so, and so on. So another example is that I'm trying to make a prediction about edges in the graph. So here the input is two nodes and their neighborhoods, and the output is whether there exists an edge, maybe an edge of a specific type in that graph. And one example that is illustrated here is, again, actually for drug discovery, where you have a network of drugs and of proteins, and you have edges if the drugs react or basically bind to the proteins, and you have edges between the drugs if you have adverse side effects if you take the drugs together. So what you're trying to predict here is basically, if I take these two drugs together, will I have side effects of a certain type that don't occur if I take any of them by themselves? And again, what I know in this case is I know something about the nodes in my graph. I have features for the nodes, and I have also types of edges, and even have different types of nodes. And a final example are recommender systems. So in this case, actually, my graph is a bipartite graph. And the two sides are basically, one side is the users and the other side is the items that users can choose. And given that the user has chosen a certain item, I would like to predict whether the user would choose specific other items as well. So here I'm trying to predict essentially from nodes to other nodes. Now, in all of these applications, what my input is, it's actually a structured object. It's a graph with side information. And I would hope in all of these applications actually to do some learning, I need a good representation of that graph, either of the graph or of the neighborhood of a node or a pair of nodes, etc. And this representation essentially should capture some information about the node labels and about the structural properties of the graph. So that's what I would like. And recently, one of the most popular tools for doing, basically computing such embeddings of nodes and of graphs, essentially simultaneously, have been graph neural networks. So let's quickly recap what are graph neural networks. Several of you must have seen them, but some of you may have not. So let me just try to explain this briefly. What are graph neural networks? So a graph neural network, and here I'm talking specifically about so-called message passing graph neural networks. it iteratively computes first an embedding for each node, and then it gathers all these node embeddings and it computes a graph embedding from that. So for the node embedding, we go in rounds or iterations, and each iteration essentially corresponds to a layer in the network. So let's say we want to update the representation of the red node here. So what we do is we gather the features of the neighboring nodes and we aggregate them by merging their information in a certain way. And that's actually the thing we're learning now, these aggregation operations. And then we combine it with the current representation of the red node. And while we are doing this for that red center node, all the neighbors are doing the same thing. And hence, in the next round, I can basically gather information about a 2-hop neighborhood. And in a few rounds down the line, I basically gather information about a k-hop neighborhood in my graph. So the sort of range of information I'm gathering increases. And finally, after a certain number of rounds, I stop, and then I take all these node representations and I aggregate them into a so-called graph level readout. So that readout is essentially just another aggregation step. And I can abstractly write these aggregation steps as essentially set functions over sets of the neighborhood features. Now, these aggregation functions have some very specific properties, and one central property is that they are what's called permutation invariant. Because there's no natural ordering between my neighbors. In a social network, there's no natural ordering between your friends. I treat all the neighbors the same way. And so hence, this is essentially an unordered set, and I apply a function that takes in unordered sets. And the same actually happens to the graph level readout. And what you're learning in these networks are the parameters for these aggregation and combine and readout functions. So to make this a little bit more concrete, let me just show you one example of what such an aggregation actually could look like. So one typical aggregation applies a nonlinear transformation to each neighbor's representation. So this is the HU k-1 of layer k-1. And then I sum them all up. So sum is permutation invariant. In which order I put the summons doesn't matter. And then I apply another nonlinearity. And what I'm learning is the function f and the function phi here. And these are essentially small neural networks, small feed-forward neural networks. So what does that have to do with neural networks? Essentially, I can view actually this iterative process as a neural network by unrolling it. So let me make this a little bit clearer with this simple example. So let's say we want to compute an embedding of that target node A. So as I said, A gathers information from its neighbors, B, C, and D. So we can write this in the following way, that we write the aggregation operation as a gray box, and then we just gather information from B, C, D. But in the previous round, B has gathered information from its neighbors, which are A and C, so we can unroll it and actually illustrate it this way. And the same has happened for neighbors C and D, so they also have gathered information from their neighbors. So let's say I had done a two iterations here. So what I'm getting is this, what's called a computation tree. And now this looks a little bit more like layers in a neural network. And what I'm learning are the shared weights of the gray boxes. So basically in each layer, I can share the weights. And these are just, as I said, simple neural networks. So I can view these rounds as layers, and that way I get actually a neural network. Now to train this neural network, each of these computation trees is essentially a training data point. And the weights are shared across the training data points. So I'm basically learning aggregation operations. And hence this is, once I know the aggregation operations, this is generalizable. I can basically feed any node and its neighborhood, any graph through this framework. So that's the main idea. So this notion of aggregation functions and this notion of computation trees will be encountered throughout this talk. So these are basically the central concepts when you're looking at analyzing graph neural networks, are these computation trees, and the gray boxes, these are the aggregation functions. So now that we know what are graph neural networks, here's what I'm going to talk about in the rest of my talk. So essentially the big question is, what and how can graph neural networks learn? And the first question is, well, what can they actually represent? Because if I cannot represent a function, there's no hope I will even be able to learn it. So first we look at representational power of graph neural networks. And then we look at also a little bit at their generalization and learning properties. So we look at generalization bounds for graph neural networks from the perspective of Rademacher complexity and from the perspective of actually an interaction between the structure of the task and the structure of the network. And finally, I will say a few words about not only generalization within the training distribution essentially, but generalization under, for example, domain shifts, and what you can sort of like some thoughts about that and some observations. So these three parts will have both theoretical and empirical observations because those sort of go hand in hand. So let's start with representational power. And one central concept when analyzing representational powers of graph neural networks has been discriminative power. So the idea being what a graph neural network actually does is it takes our graphs and it embeds them in some vector space. Now, if it takes two different graphs and it maps them to the same embedding, well, then there's no hope I could learn a function that assigns different labels to these two graphs. So it's very important to understand which graphs it can distinguish and which not. And basically for the ones which I cannot distinguish, well, these are basically living in an equivalence class from the view of the network. And to understand which graphs they can distinguish, we have to think back about how does a graph neural network actually understand or represent a graph. So we get back to these computation trees. So basically, I said what a graph neural network does is it learns an embedding for each node, and then it takes this collection of the node embeddings and it combines them into a representation for the graph. So in the best case, essentially, what we have is we have a collection of these computation trees, one for each node. And that collection of computation trees is essentially the characterization of the graph that we're using here. Now, how discriminative is that? It looks relatively unique if I look at my little example here, where you may understand the colors of the nodes here as the node features. It becomes a little bit more hairy if you look at graphs like this that are very, very regular and there's no distinction of the nodes in terms of node features. So these two graphs that I'm showing you here, they're actually different, but they would lead to exactly the same collection of these computation trees. So there are limitations and you can formalize these limitations. And in a paper published in iClear 2019, we did this. And basically the result is that these message passing GNNs, they can, at best, they can distinguish two graphs if a popular graph isomorphism test can do that as well. So this is sort of the upper bound on discriminative power, is this one-dimensional Weisfeiler-Lehmann graph isomorphism test, which also actually operates in a very, very similar way to a graph neural network. So that's the upper bound, and not every graph neural network achieves the upper bound. Whether you achieve it or not depends essentially on what kinds of aggregation functions you use. But as long as your aggregation functions are injective, you're in good shape. You can basically achieve that. So based on this view of like equating graph neural networks with a graph isomorphism test, there has been a lot of follow-up works on trying to design more powerful graph neural networks and also looking closer at their representational power. What I would like to talk about a little more is, well, I have showed you this result about the discriminative power. What does that actually mean for specific functions that we may be interested in? Is this something that's sort of like doesn't affect anything that's interesting, or is it something that affects almost everything that's interesting? So the good news is actually that the Weisfeiler-Lehmann test, out of all possible graphs, it actually is able to distinguish a very large fraction. And only a few graphs with symmetries, it fails. But what does that mean for specific functions? And I would like to generalize this result a little bit from the type of architecture I showed you to include two improved architectures that are a little bit more discriminative. The first one, and I don't want to like spend a lot of time on the formalization, just look at the pictures. The first one essentially includes a numbering of the edges at each node, and hence the neighbors are actually distinguishable that way and includes that in the message passing. The second one is for geometric graphs such as molecules, and it includes information about the angles between edges. So you can include both of these in the message passing as additional information, essentially. So now looking at this wider class of still very local message passing GNNs, let me pose the following question. Can GNNs learn to identify specific structural graph properties? So this is, for example, the length of the shortest cycle. Does it have any cycles that are conjoined, meaning cycles that share an edge? Can it compute diameter, where diameter is calculated via shortest path distance, etc.? And these are actually properties that we care about when we try to embed molecules. I just saw there's a question. I'll answer this question soon. So the molecule, if we want to learn functions of molecules, actually its functional groups are very important. And that's where we actually need these kinds of features. And unfortunately, there's a negative result, meaning in general, these message passing graph neural networks cannot learn such functions. So you can basically find graphs where that fails. And the same holds actually for these generalizations that I showed you. A very similar result was actually proved by one of the co-organizers of this workshop. So they showed that graph neural networks cannot actually count motifs of size 3 or larger. So that's very similar, and these are negative results, how like basically this message passing fails to represent certain structural properties. So let me give you an intuition why that happens by showing you an illustrative sketch of the proof. So the proof basically goes as follows, that we try to find two graphs that differ in the structural properties. So think about the shortest cycle. These two graphs, the first graph is sort of two graphs in one. They have different shortest cycles, and the colors here denote the node features. So what happens is essentially that for these two graphs, even though they're different, I get the same representation. So and as an example, let's look at this, the representation, the computational tree of this node B1 here. And if you basically write it out, these are the computation trees you will find, and they are exactly the same in terms of node features. And the same happens for all the other nodes in the network. So basically there's no way you can distinguish the two graphs via the representation of the message passing graph neural networks. That's the idea. So basically these graphs have enough symmetries that you cannot identify them, and hence you will always assign the same label to these graphs. So you cannot learn a function like shortest cycle. So now I've talked a bit about representational power. I showed you one negative results. Now I will want to show you a little bit more about learning with GNNs when they can actually learn the function. But before that, let me just try to answer some of the questions that were posed here. So the first one was, how much does the injective activation assumption affect the results? So what happens if we use ReLU activations? That's okay. So the thing is, it's not actually the activation functions, but it's the entire aggregation function. So basically I take a set of these representations of my neighbors and I map it to some output, to a vector essentially, and that function has to be injective. So basically different sets of neighborhood features have to map to different vectors. So that has to be injective, and in fact multi-set. So you have to take into account the multiplicities. And you can achieve that with ReLU networks. And in fact, all you need is essentially a nonlinear transformation of the neighbors, and then a sum aggregation and another nonlinear transformation. And these nonlinear transformations have to be injective, and that's enough to have an injective function. So you can do it with ReLU networks. And the second question is, can GNNs be used to compute other metrics such as centrality. I think you can compute some of these. So some of these can be computed via message passing. I'm not sure you can compute all of them. So for centrality, I believe you could compute some properties that have to do with eigenvectors, because eigenvector computation you can write essentially in a message passing form. But I haven't formally written it out, so this is basically what I think should be doable. Yeah, but it needs a little bit like thought and proof. Okay, so let me get back to the talk. So let's turn over to generalization with GNN. So there have been several generalization analysis of neural networks, and I'll first talk a little bit about Rademacher bounds. So there have been, for example, bounds for feed-forward neural networks, but now GNNs are different in the way that they actually correspond to structured networks. So they are very local, more like CNNs, but their degrees vary. And then different from CNNs, they actually have these aggregation functions that are permutation invariant. CNNs, you could essentially view the convolution as an aggregation function, but it's not permutation invariant. It actually matters who's your left and right neighbor. They are typically treated differently. So that's the difference. So what would happen for GNNs? Can we take that into account? So here we make the setup a little bit more specific. So the GNN family that we look at are those with so-called mean field update that have been used a lot in chemistry. So you have the aggregation operation, just that I said you actually have a nonlinear function G, and then you do a sum aggregation, and then you have another nonlinearity. And then you combine that with the current actually input node feature. So that's XV. And the phi is again a nonlinearity. And then the way we do the aggregation over the node embeddings is that we basically average them. So basically we have each node make a prediction and average that. So now let's look at, that's sort of the model class we're looking at. And now if we look at generalization bounds, there's of course a lot of theory on this. So here's one generic bound that says basically it's for margin-based loss. But that says if I'm giving the samples, I look at the empirical risk or the training loss, and the difference between the training loss and the probability of making an error in the test set is bounded by the Rademacher, basically a complexity measure of my function class, plus a term that shrinks with root m with a number of samples m. So now the important thing to bound here is that Rademacher complexity, and it essentially looks like this. It basically measures how well can your model fit arbitrarily sampled random or Rademacher random variables, basically these epsilon i's or -1 + 1 variables. So this complexity in general is non-trivial to compute. When we look at graph neural networks, we have to think back again, how do they actually compute their embeddings? So again, they are doing the computation tree. So basically they have the collection of the node embeddings, and each node embedding corresponds to one of these computation trees that corresponds to how it's computed. So we should probably be using that. And in fact, you can use it very usefully. So what one can show is that the Rademacher complexity of the entire GNN can be bounded by the Rademacher complexity of predicting from any computation tree. And now the parameters of that tree, sort of the complexity parameters, essentially are the network depth, which means the depth of that tree, how many iterations of message passing I'm doing, and then the spectral norm of the weight matrices that I'm using in my aggregation functions. So these are two of the parameters. Now, the other thing is that we have that permutation invariance that still has to come in somewhere. And that comes in the aggregation functions. Now we have to sort of analyze the complexity of these aggregation functions. And there we can use the following result, that any of these aggregation functions can be universally represented essentially in the following form, that for each of the items, basically x, the little x here are the features of the neighbors. we apply a nonlinearity, we sum them up and apply another nonlinearity. And now looking at the sum, looking at the complexity of the sum, another complexity parameter will be the degree of the graph, or basically the branching factor of the tree here. So these are the parameters that will affect our complexity. And that's the main idea. Skipping all the calculations, you reach at the following bounds. So here we actually have 3 bounds, and they depend on what I called here the percolation constant, meaning a combination of the spectral norms of the weight matrices and the Lipschitz constants of the nonlinearities that you're using. So they depend on the network depth L, the number of samples M, the embedding dimension R, and the degree D of the graph. And if you compare this to VC-based bounds that were proved previously, in most cases, these bounds here are a bit tighter because the VC dimension bounds, they have this capital N, and capital N is the number of all nodes in your graph, which can be pretty large. So there's another interesting thing to note about these Rademacher bounds. So one thing is that relatively nice is they depend linearly on the depth and the degree. If you compare them to Rademacher bounds for RNNs, there's actually only one difference. So they are pretty similar, except that they have the additional factor D, which is the degree of the graph. So now essentially that means that the RNN is essentially like a line graph or a tree with branching factor 1. And the GNN is a generalization of that. So in that respect, these bounds actually match pretty closely. So that was basically for a Rademacher analysis, but and that is for functions you can learn. In practice, what also often counts is what kinds of tasks are you actually learning? And one interesting question is, how does the structure of the task interact with the learning of a network? So even if you can represent a task, how well can you actually learn it? So I want to talk a little bit about that. Before that, I saw there's a question, and the question was, can you compare it to message passing in Bayesian networks? Right, if nodes represent variables, that's right. So basically, this is like a message passing algorithm, and you can actually equate it essentially to message passing in graphical models, right? And there's actually a nice paper by Le Song and his group where they do exactly that. So let's go back to the structure of the task. And here I want to look at specifically the question of learning graph algorithms or learning algorithms. So here I called it reasoning tasks. So reasoning tasks in general have been tasks where the input is a collection of items that with their features. So we are abstracting away here all the actually understanding the visual representations, which is a big deal, and that is sort of a different step. So here we are simplifying that we are given a universe of items, a set of item descriptions essentially, and we are asking the neural network to answer a relational question about these items. And this question could just be simple, like what is the maximum value difference among the items that I've given? A neural network has to learn to compute an answer. Or something like, oh, this is actually, these items have distances and I'm actually trying to compute the shortest path. And the neural network has to learn to compute shortest paths, which is a much harder question, sort of like an iterative relational reasoning question. So all of these are essentially like algorithms. So here we are trying to learn essentially to mimic algorithms. Now, the main question when we try to learn to mimic algorithms of this sort, basically answer questions about a set of items. How do we represent this universe of items? And now there's various ways you can do this. The first simple thing is that each of my items, I consider it basically an input vector, and I just concatenate these vectors and I put them into a simple feed-forward network or NLP. The disadvantage of this thing is that the order matters. So if I put them in different order, the input looks different. I have to actually learn to ignore that. Hence, there's a different family of models, which are called deep sets, that are by design permutation invariant. So the order doesn't matter. And the idea is that you apply a transformation to the features of each of your items, and then you sum them up. So again, you have basically a sum aggregation, and then you apply another neural network to it. And another recently popular idea was, well, I could just view these items as a fully connected graph. So I just make this a fully connected graph. I put edges, and then I apply a graph neural network to this. So the graph neural networks that have been used here have a specific structure. So they're still the message passing algorithms, but the aggregation operations are as follows: that the representation of item S here, what I do is I look at the pair of S, the center item, and each of its neighbors, and I compute a pairwise function for each of them, and then I sum up the results of these pairwise functions. And this is what I do iteratively. So this is how my aggregation operation works. It's just that I specifically take into account the center node. And then I do the final aggregation of the graph just via sum. So now, if the function you want to represent is permutation invariant, all of these three architectures essentially have the same representational power. But when you do learning with these architectures, you see big differences in actually the difficulty that they have to learn these kinds of combinatorial tasks. And what we were basically trying to do is to find a formalization for this phenomenon, which you could call like architectural inductive bias, for example. And the idea is the following, that if you look at these different architectures, they sort of imply a computational structure for the function. Each of these gray boxes is like a little feed-forward neural network, and you're arranging them in a certain way. So now we basically think about the complexity of these little gray boxes. And that's what sort of enables the learning. And essentially the idea is, how well does this arrangement of gray boxes align with the structure of the algorithm that would compute a solution to your problem? So basically, in a nutshell, we call this algorithmic alignment. Basically, if the network can mimic an algorithm for solving your task, such as shortest path, via basically putting a few simple functions into these gray boxes, then the network should be able to learn this task well. And if not, so if you just look at the feed-forward neural network, it has to learn a lot of the structure of the task from scratch. So that should be much harder. So that's the hypothesis. So let's look at this at a few examples to illustrate this a little bit. So the first example is very simple. It's basically, what is the maximum value difference between any of the input items? That's the thing that the neural network should be computing. So one simple algorithm for computing this is compute all pairwise distances or differences and find the maximum. So now if you look at the graph neural network, I told you, like, essentially it's doing pairwise operations, and then it aggregates these pairwise operations. So it essentially exactly matches the structure of this algorithm. So step one would basically be the pairwise operations, and step two would be the aggregate, like the summing up the aggregation by doing a softmax. For just the feed-forward network, it's a bit harder because it has to learn to be permutation invariant. It has to learn to first do pairwise distances. So it's much harder to actually learn the structure. Now, what happens for the deep sets? You do something at each item, and then you sum up over all the items. So certainly doing these pairwise operations is not that easy to implement with this. You have to learn to ignore a lot. But there's a different way you can actually solve the task. By basically saying I compute the min of everything and the max of everything, and then I just take the difference of these two. And this is something you can easily do by looking at all of them simultaneously. So hence, we would conjecture that the deep sets and the graph neural networks can learn the task easily, but the MLP cannot. And that's essentially what we observe. So here are the accuracies for the different models for a relatively small task. And we see that MLP actually cannot do it, and the other architectures essentially succeed. If you order the input of the MLP, no surprise, it can actually learn it because it just has to learn to basically subtract the first from the last item. So this was a fairly simple task. Let me show you something that's a bit harder, and that's shortest path. So one way to compute shortest path is by using the Bellman-Ford algorithm, and that is an iterative algorithm that and in each iteration, we have a state of each node, and the state of each node is basically the current distance to the target. And in each iteration, each node just says, well, if I would go via this particular neighbor, would I actually get to the target quicker? And so you update basically the state by looking at each of the neighbors individually and see whether you could actually find a shorter path by going on each of these neighbors. Now, if you look at the computational structure of a graph neural network, it exactly mimics this kind of algorithmic structure. So for each iteration, we go through all the nodes and update the states of all the nodes. And all you really have to learn is that your aggregation function does this min over all the neighbors, summing up two things and doing the min over all neighbors. That's a relatively simple operation. So we would expect actually that a GNN can learn this very well. And what we see empirically is that this is the case, but only for sufficiently many layers. And now if we assume that basically each GNN layer corresponds to an iteration of the algorithm, well, for computing shortest path, you in principle have to first take a number of iterations that corresponds to the number of the nodes, or basically the length of the shortest path. And here, what we see is actually the shortest path was length 6 or 7. So a GNN with 3 layers actually is pretty good. And that is, you can achieve if you do the Bellman-Ford bidirectional. So again, this observation agrees with the hypothesis that sort of the structural alignment tells you something about how well can the network learn the algorithm. And more generally, actually, GNNs can actually mimic dynamic programming updates of the form that I just wrote here. So basically in each iteration, you update using the prior states of your neighbors. And many of the tasks that people essentially have considered in these reasoning tasks are of dynamic programming form. They have exactly these update forms, and hence it makes a lot of sense that GNNs actually can learn these very well. So this is sort of an empirical and intuitive explanation for why GNNs should be able to learn many of these algorithmic tasks very well. Can we also formalize this? So here's an attempt to formalize it. So we say, and so for that, doing that, we try to formalize the notion of algorithmic alignment. So we say a neural network aligns with an algorithm if it basically can mimic this algorithm via a small number of these modules or gray boxes in my pictures. And each of these boxes or modules is learnable with a small number of data points. So basically simplicity measured as sample complexity. And if this is the case, and by learning, basically, I mean learning in a PAG framework, that with high probability, I'm matching the function almost everywhere under my distribution. So if this is the case, then the network can actually learn the task fairly well with essentially a relatively small number of samples. So that is sort of a first initial theoretical step to try and formalize this notion of architectural inductive bias and how the sort of structure of the task aligns with the learning of the network. So now in the last few minutes, I would like to go from generalization within data to generalization going beyond the training data that we've actually seen. And I would like to focus on the case of graph neural networks again. So why is this relevant? If you think again about the task of learning algorithms, say we want to learn the shortest path, or we want to learn to compute the maximum degree in the graph. If I train my graph neural network on a collection of graphs, I would hope that, for example, it also generalizes to larger graphs or to graphs with different degrees. If I'm actually learning that algorithm, it should be able to do that. So the question is, would it be? And to think about that, again, let's think about these computation trees and how GNNs are actually built up. So again, we have these aggregation functions, and each of the aggregation functions is essentially a small feed-forward neural network. So what do we know about the extrapolation properties of feed-forward neural networks? And let's say ReLU networks, because we're using ReLU networks. So here is basically what happens, and we know, of course, ReLU networks implement piecewise linear functions. And so here, this is a very simple illustration where we have a small set of training data, and then which is just a cosine function. And we look, what does the network do outside of the training data? And essentially it extrapolates piecewise linear functions. So it basically puts a lot of the nonlinearity just into the training data, fits it perfectly, does a perfect approximation within the training data, but outside the training data, it looks pretty much piecewise linear. And this happens also in multiple dimensions. So the dark part here is the neural network extrapolation. And of course, it doesn't really, like, you don't have any training data there. Anything is sort of as good as anything else. So you're using basically what the architecture, the bias of the architecture is. That's essentially what's happening, and the learning algorithm. So what you actually can show is that as you go away from the training data by, like, say, in a scaling the vector v with a factor t, then you basically, with convergence speed O of 1 over t, you converge to this linear function. Okay, so this is for ReLU network. So what does that mean in terms of graph neural networks? So these are sort of now our aggregation functions. This is how they behave. Now let's look again at the shortest path example. So what we want to learn is an aggregation function that does this sum and minimum. And we can implement this with a sum aggregation and an MLP by basically having the MLP learn a nonlinear function. And then we can mimic it. So your MLP is a universal approximator, and with the sum, you can actually mimic this. Unfortunately, what will happen if your inputs are out of range? Basically, you have some distribution shifts and you're going away from what you have seen in the training data. Then if you think about the picture on the previous page, you would actually no longer implement a nonlinear function. You would do something linear. But people have observed actually that GNNs can generalize across different graphs. But what they used was actually not the sum MLP, but they used the min MLP for shortest path. And now if you think about the min MLP, all the MLP needs to implement here is actually a linear function. So now if you connect this observation with the observation on the previous page, well, basically for interpolation, for learning sort of with the same training and test data, it doesn't matter which of the two, but for the extrapolation, it matters which of the two aggregation functions you actually use, because one presumably is better able to continue, basically one has to continue nonlinear function and one has to continue linear function. And this is actually what you see empirically too, that interpolation, both of them work fine, but if you go do extrapolation, so you look at graphs with different degrees and different sizes, then actually the sum pooling does much worse than the min pooling. And this is a phenomenon you observe also for max degree, which has the same problem, that you're basically learning a max operator. If you implement it and hard code the max operator, it actually extrapolates better. So as long as sort of here, your extrapolation just requires a linear function, you're okay. Otherwise, you would actually need too much prior knowledge. Now, this is the aggregation function is one factor that affects your extrapolation. Another factor that affects it is the distribution of graphs in the training data, because still you need sort of enough information in the training data about the diversity of structure and degree in the graphs that actually helps you extrapolate to different graph structures. So this plot, what it shows is that in different cases where the training data set was, for example, just path graphs, just tree graphs, etc., and you try to extrapolate to general graphs. And you see there's actually a big difference in the extrapolation performance between these different graphs. So this is something one can actually also formalize. So here's a relatively simple formalization for the case of max degree. So proving actually that GNNs with if you do a sum aggregation, you cannot actually extrapolate max degree to graphs with different degrees. But if you use a max aggregation, so you basically put the max in the aggregation instead of a sum, then you can learn the max degree under certain conditions of the data. So this analysis was actually done with the NTK regime, so the neural tangent kernel. So that's why sort of for this proof to work, you have to be in that regime, and you also basically need specific conditions on your data, on the degree distributions of your data. It's actually a very simple condition on the data. And basically you have to have enough support to span R4. And you get actually similar results if you do not only extrapolation with degrees of the graphs, but also change the distribution of the node features. You observe actually kind of similar phenomena. So with that, I would like to conclude my sort of journey through the learning with graph neural networks. So we started with just the representational power of message passing GNNs and saw some limitations in terms of structural graph properties. And that really raises the question sort of, what are graph neural networks that represent the functions that we are interested in the most compact way? The second question are generalization bounds. So we saw actually there's a lot to think about in terms of taking into account the specific structure of GNN, so the computation trees, the permutation invariants, but also the interaction between the task and the data distribution and the model itself. And finally, this matters not only for interpolation, but also for extrapolation. So where really the nonlinearities and the aggregation functions start to matter even more. And many of the analysis I showed you sort of are trying to sort of theoretically explain phenomena that we observe in practice, but I think there's still a lot to do in terms of tightening the results, making them more general, etc., etc. So thank you very much for the attention, and I'm happy to take any questions now.
Thank you very much, Stefanie. That was a fascinating talk. We have one question from the Q&A. I see you see it. The compute pairwise for the computing the pairwise distances. It's been a week. How would this scale for graphs with trillion plus nodes?
Yeah, that's a very good question. So basically, a lot of the tasks that, like these reasoning tasks, people have considered, the number of items was actually pretty small. So like doing all pairwise distances is not a problem. If you actually have a trillion plus items, you probably don't want this quadratic computation. But what you may have is some other locality information. So for example, people have also used neural networks to do simulations, say for like particles, how they move and how they interact. But there you have locality information. So you can actually restrict your graph to essentially the local neighbors. And then you can just do computations more locally. That would make a lot of sense in that case. And I think more generally, if you actually know like some locality or some other similarity, and you can basically do just the nearest neighbor graph within some radius or so, that'll definitely help. If you don't have that, you may have to do some sampling or sketching or so. People have tried that also to scale up GNN, so that may be a possibility here, but I don't know what that would actually do with the results in practice. I don't know. Okay, I see there's another question. So can you model convolutional layers with a GNN? So basically, yeah, the exact difference is the invariance. So the permutation invariance. So convolutional neural networks do not have permutation invariance. You treat each neighbor differently. But in principle, what you could do is if you actually could identify each neighbor. So basically the restriction is that if I give you the same graph as an input, again, you want to have the same output ideally. Otherwise, it's a little bit tricky because for the same input item, you may have two different outputs. So basically you can, if you have a way to identify your neighbors, make them identifiable, you can learn a function basically that where in the aggregation step you also take into account the identifier of the neighbor. And essentially this port numbering neural network that I showed you does essentially something like that, with a restriction that the labeling is actually of the neighbors is actually not unique. The other difference to CNNs is that in CNNs, typically the degrees are the same. So basically in an image, you always have the same number of neighbors. Each pixel has the same number of neighbors. In a graph, that's not necessarily the case. So the degrees vary a lot unless you have a very regular graph. So you need to still have a function that is able to basically accommodate a small number of neighbors and a large number of neighbors. So you can still mimic the convolutional layers, because that would just be a regular graph where you identify the neighbors, and you could, in principle, just say, I have these neighbor IDs. So each neighbor basically has like, this is my left neighbor, this is my right neighbor, and I take this as input. So you could actually model a CNN with a GNN. But you could not as easily model a GNN with a CNN. Yeah, that's the long answer.
Thanks. Do we have any questions from the panelists?
Yes, hi, very nice talk. I have a question. So these negative results on the representational power often depend on graphs that are highly symmetric or regular. And is there a notion for which you can say that the representation of the representational power of these graph neural networks is increased if you consider a model of graphs that do not have those properties?
I believe so, because even if you look at the Weisfeiler-Lehmann test, it only fails like for very specific graphs. So basically, if you exclude these graphs, it solves the graph isomorphism test. So I believe if you basically say, I restrict myself to a distribution of graphs where certain symmetries don't happen or super unlikely to happen, then these failure cases don't happen. So that should be much better. What happens to like doing, basically, if you want to actually compute these small structural properties, you basically, even if at a local level you have these symmetries, you may run into trouble. I haven't thought through it, but it may be that actually locally you also have to sort of allow not too many symmetries.
And the complexity bounds that you use for the second part of your talk, do those depend on the models of graphs? It's like the representational power close to graphs that are close to regular have a different complexity than the ones that are genetic?
You mean in the learning bounds?
Yeah, or in any of the parts that you discussed.
Yeah, so definitely, I mean, for the discriminative power, it definitely is the case that the symmetric graphs are the ones where you fail, because these are the ones where the computation trees match. For the learning theoretic results, we don't actually specifically take into account any of the symmetry in the graph. That's though a very interesting question. So that assumes that basically you will be able to represent the function. But whether you would actually have more trouble learning with more regular graphs, that may be the case. So one case where we actually observed is if you look at this extrapolation, that's kind of very intuitive. If you only learn, say, with graphs of degree 3, then computing the max degree is kind of a function that's constant 3. But then that definitely doesn't generalize to any other graphs other than 3 regular graphs, for example. So if you look at sort of the results for like when you train, these are the shortest path results, when you train on a certain graph structure and then you try it on different graphs, there it makes a lot of difference how sort of diverse the structure of your input graphs is, or the degrees of your input graphs, etc. So that's where it plays a role. And it sort of comes into play when you look at, so this, like my lemma down here that has a condition on the data that basically there has to be enough variety in the min and max degree in the number of nodes that have the min and max degree. That comes into play, but I'm sure there's more to say in that direction.
And does it come into play like the difference on the min and the max? Like say if the difference is like 1 or 2, then your approximation is much worse than if the difference is large?
Yeah, so this result doesn't actually look at the difference. It just says that basically you need some variety. It's probably the case that that also matters. I don't have a specific result about that, but I would think that sort of the more different ones you see, the more you may actually be able to adapt to that. Yeah. So I think there's a lot of open questions still how the actual structure or the distribution of the structure of the graph interacts with the actual learning performance of different tasks.
Thank you.
Any other panelist questions? I have a quick question while we still have a few minutes.
Mm-hmm.
I was really intrigued by the slide that you had that showed the 3 layers of the algorithm followed by the performance as you increase the number of layers of, up till you get to, about 90% with 3 layers, which matches the number of layers in the matches the number of stages in the algorithm. But then the performance went up a little bit after that, 94%, 95%. I was curious if you've kind of dissected that and figured out in the 4, 5, 6 layer versions of the graph that you learned, where the different stages of the algorithms reside and what's kind of the difference in terms of, the particulars of what the algorithm is actually doing and what the approximation that's learned through the graph neural network is learning. And if you can quantify kind of that difference in any meaningful way.
Yeah, that's a very interesting question. So I don't have any good conclusive analysis about that. Like that's the natural next question. Like, do you actually, so this is sort of the hypothesis that you're essentially mimicking something like that. And the fact that you can do it with 3 onwards, roughly, like where you can do the bidirectional Bellman Ford is sort of an indicator for that, but it's of course like not a proof. So we don't have any more specific analysis, like actually checking that in more detail, which would be a very interesting thing to do. Yes.
Thank you.